What if I told you that right now, inside every atom in your body, forces are at work that could power entire civilizations? That somewhere in the cosmos, explosions are happening that make our sun look like a flickering candle. Today, we're embarking on a journey to discover the most powerful forces in the universe, phenomena so extreme they challenge our understanding of reality itself. From the tiniest quantum interactions to cosmic events that span billions of light-years, we'll explore 8 incredible forces that shape everything we see. By the end of this video, you'll understand how these cosmic powers not only created the universe around us, but literally forged the very atoms that make up your body. So buckle up, because we're about to witness power beyond imagination. Let's start with something invisible yet incredibly powerful happening right inside you. Every atom in your body contains a nucleus where protons are packed together. Here's the problem: protons all carry positive electric charge, and like charges repel each other violently. So why don't atomic nuclei just explode apart? The answer is the strong nuclear force, and it's exactly what it sounds like. This force is roughly 100 times more powerful than electromagnetism and an almost incomprehensible 10 to the power of 38 times stronger than gravity. If gravity were a whisper, the strong force would be thunder that could level mountains. But here's what makes it truly bizarre: the strong force works through particles called gluons, and the harder you try to pull quarks apart, the stronger the force becomes. It's like a rubber band that gets thicker and more resistant the more you stretch it. This means you can never isolate a single quark. Try to pull one out, and you'll just create new particles instead. The strong force operates at distances smaller than a proton, that's about 1 femtometer, or 1/4,000,000th of a meter. At these scales, our everyday understanding of physics completely breaks down. Yet without this force, atomic nuclei couldn't exist, stars couldn't shine, and the universe would be nothing but a cold soup of hydrogen and electrons. Think about that: the most powerful force in nature has the shortest reach. It's like having an incredibly strong bodyguard who can only protect you if you're standing right next to them. Now let's scale up dramatically. Imagine a star 50 times more massive than our Sun, burning through its fuel at an incredible rate. When such a monster finally dies, it doesn't go quietly. Instead, it creates what we call a gamma-ray burst, the most powerful explosion the universe can produce. For just a few seconds, a single gamma-ray burst releases more energy than our Sun will produce in its entire 10 billion-year lifetime. These cosmic beacons are so bright that if one occurred in our galaxy, even thousands of light-years away, it would appear brighter than the Sun in our sky and could potentially strip away Earth's ozone layer. Here's how they work: when a massive star collapses, it forms a black hole almost instantly. But if the star is spinning rapidly, something incredible happens. The collapsing material creates jets of matter and energy that shoot out from the poles at 99.9% the speed of light. These jets are so focused they maintain their beam-like structure across millions of light-years. The most powerful gamma-ray burst we've ever detected was nicknamed BOAT, the brightest of all time. It occurred in October 2022 and was so intense it temporarily blinded our space-based detectors and actually affected Earth's atmosphere from 2 billion light-years away. That's like someone lighting a match on the moon and having it visible from Earth. These events are essentially cosmic lighthouses, sweeping beams of destruction across the universe. The scary part? We'd have no warning if one pointed directly at us. The deadly radiation travels at the speed of light, arriving at the same time as the light that would let us see it coming. Speaking of cosmic monsters, let's talk about black holes, regions of space where gravity has won the ultimate victory. At the center of our own galaxy lurks Sagittarius A, a black hole containing 4 million times the mass of our Sun. But that's actually considered small in the cosmic scheme of things. The largest black holes we've discovered contain over 40 billion solar masses. That's like cramming 40 billion suns into a region smaller than our solar system. The gravity around these objects is so intense that space and time themselves become warped beyond recognition. Here's what's truly mind-bending: near a black hole, time literally slows down. If you could somehow survive falling toward one, you'd watch the universe age rapidly around you as your own time crawled to a halt. From your perspective, you might fall in normally, but outside observers would see you freeze at the event horizon, your image slowly fading and reddening until it disappeared. But black holes aren't just cosmic vacuum cleaners. The most active ones are surrounded by swirling disks of superheated material that glow brighter than entire galaxies. Some launch jets of particles at nearly light speed, creating beams that stretch for hundreds of thousands of light-years. These jets carry enough energy to heat entire galaxy clusters and can prevent new stars from forming across vast regions of space. The most distant black holes we can see formed when the universe was less than 1 billion years old. How they grew so massive so quickly remains one of astronomy's greatest mysteries. It's like finding a fully grown oak tree in a forest that was planted yesterday. Now let's discuss perhaps the most mysterious force of all. Right now, as you watch this video, every galaxy in the universe is racing away from every other galaxy at an ever-increasing speed. The force driving this acceleration is called dark energy, and it makes up about 70% of everything that exists. Here's what makes dark energy so strange: unlike every other force we know, it doesn't weaken with distance. In fact, as the universe expands and more space is created, more dark energy appears to fill that space. It's like a cosmic gas pedal that only knows how to accelerate. We discovered this by accident in the 1990s. Scientists were studying distant supernovae, expecting to find that the universe's expansion was slowing down due to gravity. Instead, they found the opposite: the expansion is speeding up. It was like throwing a ball in the air and watching it accelerate away from you instead of falling back down. Think of the universe as a balloon being inflated by an invisible breath. Dark energy is that breath, causing every point on the balloon's surface to move away from every other point. Galaxies ride this expanding space like boats on a swelling ocean. The implications are both fascinating and terrifying. Dark energy appears to violate one of physics' most fundamental laws: conservation of energy. As space expands, the total amount of dark energy increases, but where does this extra energy come from? We simply don't know. In the far future, dark energy will tear apart everything we see. First, galaxy clusters will separate beyond recognition. Then individual galaxies will lose their gravitational grip. Eventually, even atoms themselves might be stretched apart in what scientists call the Big Rip. The gentle force that's slowly expanding space today will become the universe's final destroyer. Imagine taking Mount Everest and compressing it down to the size of a sugar cube. The result would still be 1,000 times less dense than a neutron star. These cosmic lighthouses pack more mass than our Sun into a sphere just 12 miles wide, creating some of the most extreme conditions in the universe. A neutron star is what's left when a massive star explodes as a supernova but isn't quite massive enough to form a black hole. The explosion blows away the star's outer layers, but the core gets compressed so violently that protons and electrons are literally crushed together to form neutrons. The result is essentially a giant atomic nucleus the size of a city. The surface gravity on a neutron star is about 200 billion times stronger than Earth's. If you could somehow drop a marshmallow from waist height, it would hit the surface with the energy of a hydrogen bomb. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. That's like compressing Mount Everest into a sugar cube. But gravity isn't even their most extreme feature. Neutron stars have magnetic fields up to 1 trillion times stronger than Earth's. These invisible force fields are so powerful they could erase every credit card on Earth from 600 miles away. The strongest ones, called magnetars, have magnetic fields so intense they affect the very structure of space itself. When neutron stars spin, and some rotate 700 times per second, they become cosmic lighthouses called pulsars. They sweep beams of radiation across space with the precision of atomic clocks. These beams are so regular that when they were first discovered, astronomers briefly wondered if they might be signals from alien civilizations. The most violent neutron stars occasionally experience starquakes, cracks in their ultradense crusts that release more energy in 1/10 of a second than our Sun produces in 100,000 years. These magnetic explosions can be detected from across the galaxy, demonstrating the incredible power contained within these stellar remnants. Some of the most spectacular displays of cosmic power occur when massive objects collide. Let's start with something that happened 130 million years ago but made headlines in 2017, the collision of two neutron stars. Picture two objects, each containing more mass than our Sun but only 12 miles across, spiraling toward each other at thousands of miles per second. As they orbit closer and closer, they create ripples in spacetime itself, gravitational waves that stretch and compress space as they race outward at light speed. In the final moments before collision, these neutron stars complete hundreds of orbits per second, whirling around each other faster than a helicopter blade. When they finally touch, the collision is so violent it literally shakes the universe. The gravitational waves from this event were detected by instruments on Earth that can measure changes in distance smaller than 1/10,000th the width of a proton. But the collision does more than just create gravitational waves. The extreme conditions forge elements heavier than iron through rapid neutron capture. A single neutron star merger produces several Earth masses worth of gold, platinum, and other precious metals, hurling them into space at 1/3 the speed of light. The gold in your jewelry, the platinum in catalytic converters, even the uranium in nuclear reactors, all of it was forged in the violent embrace of colliding neutron stars billions of years ago. You're literally wearing stellar ashes created in some of the most powerful explosions in the universe. On even larger scales, entire galaxy clusters, each containing thousands of galaxies and trillions of stars, sometimes collide with each other. These cosmic crashes release more energy than all the stars in both clusters combined, creating shock waves that heat gas to temperatures exceeding 100 million degrees and generate radio emissions spanning millions of light-years. But all of these incredible forces pale in comparison to the event that started it all, the Big Bang. 13.8 billion years ago, everything that exists today, every atom, every star, every galaxy, was compressed into a point smaller than a proton. This wasn't just the beginning of matter and energy, it was the beginning of space and time themselves. In the first fraction of a second, something called cosmic inflation occurred. The universe expanded faster than light itself, growing from smaller than an atom to larger than a grapefruit in less time than it takes light to cross a proton. This expansion was so rapid it defies human comprehension. Imagine a single atom suddenly becoming larger than our solar system in less time than light could travel across that atom. The energy involved was truly staggering. In that tiny fraction of a second, more energy was released than has been produced by every star in the observable universe over the past 13.8 billion years. This energy went into creating new space and filling it with the matter and radiation we see today. During these first moments, the temperature was so high that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, unimaginably powerful interaction. As the universe expanded and cooled, these forces separated in a series of phase transitions that determined the basic structure of physical law. The Big Bang wasn't an explosion in space, it was an explosion of space itself. It created time as well as matter, establishing the laws of physics that govern everything from quantum fluctuations to galaxy formation. No event before or since has matched its power to create everything from nothing. What's even more remarkable is that tiny quantum fluctuations during inflation were stretched to cosmic scales, becoming the seeds of all large-scale structure in the universe. Every galaxy, every star, every planet, including Earth, owes its existence to quantum ripples that occurred when the universe was smaller than an atom. We've journeyed from the quantum realm to the cosmic scale, witnessing forces that stretch the very limits of what reality can contain. But here's the most remarkable truth: we're not separate from these cosmic forces, we are their direct products. The calcium in your bones was forged in stellar explosions. The iron in your blood was scattered by dying stars. The gold in your jewelry was created when neutron stars collided in violent embraces that shook spacetime itself. The oxygen you breathe was manufactured in the cores of massive stars that lived fast and died young billions of years ago. We are literally made of stardust, assembled by forces so powerful they can create and destroy entire worlds. Yet here we stand, conscious beings capable of contemplating our own cosmic origins. The universe has been working for 13.8 billion years to create the conditions necessary for you to exist and understand your place in this cosmic story. Every force we've explored, from quantum fluctuations to galactic collisions, played a role in bringing about this moment when you can comprehend the very powers that created you. The strong nuclear force holds your atoms together. Stellar explosions created your elements. Gravity shaped the cosmic web that allowed galaxies to form. Dark energy continues to expand the stage on which this cosmic drama unfolds. What's the most powerful thing in the universe? Perhaps it's not any single force, but the universe's inexhaustible creativity, its ability to transform simple hydrogen into stars, stars into heavy elements, elements into planets, and planets into the stage where life and consciousness can emerge to contemplate the very forces that brought them into being. The next time you look up at the night sky, remember that you're witnessing an ongoing battle between cosmic forces that have shaped everything you see. And remember that you, made of stellar ashes and quantum dreams, are not just an observer of this cosmic drama, you are one of its greatest achievements. In understanding these cosmic powers, we become the universe awakening to its own magnificent potential. That might just be the most powerful force of all. And that's a wrap on today's journey through the darkest corners of the universe. From black holes to the edge of the observable cosmos, there's still so much we've yet to discover, and we're just getting started. If you enjoyed this cosmic adventure, don't forget to like the video, share it with your fellow space lovers, and subscribe to the channel for more mind-blowing content like this. And hey, hit that notification bell so you don't miss the next episode as we continue to explore what lies beyond. Got questions or your own theories about the universe's mysteries? Drop them in the comments, I'd love to hear your thoughts. Until next time, keep looking up, the universe is waiting. Let me know if